Well, good day. My name is Rob Sellis. I'm the CEO of Akit, and today I'd like to give you a bit more insight in the specifics of composite tubulars for downhole applications and bring out some factors that are important and relevant because engineering in composites is just a bit different than it would be in steel. First, I'd like to give you a short introduction of the company, where we come from, and then discuss the common traits of all composite tubulars. What do they have in common? That will give you an idea of the specifics against traditional metallics. Then I'm afraid I'll have to bother you with a bit of composite theory on how composites work. And then I'll focus in a bit more about the importance of the orientation of the fibers, which we call the fiber layup. After that, I'll take you through the importance of voids in the structure of composite. And then I can demonstrate why Akit's tubulars are actually different than other composite tubulars, and how they deliver a fantastic result, especially when it concerns the orientation of the fibers and the void content. And I'll summarize at the end. Just introducing Akit to you. Akit is a Dutch company from the Netherlands, which after more than 10 years of R&D successfully installed a composite tubular system in the Middle East at 16,000 feet of depth, which thereby set a world record. Following that, we started automatic production facility in 2015 in the town of Lelystad in the Netherlands. And from there, we delivered our first orders to customers in 2017. Akit nowadays is developing the company further, and we are looking to produce and optimize those products that are going to help you. Now, the biggest issue is, of course, corrosion. We all know corrosion, and we know how it sacrifices the well integrity and the cost that we have to incur to combat corrosion, to monitor the state of the installation, the workovers, the people that are involved, the organizational complexity, are all things we can do. This slide is a typical picture of a well which suffers from corrosion, and as we all know, you as operator will be held responsible for what's going to happen with these wells. Now, composites present a solution here. And composite tubulars, although they vary in materials that are used and how they're put together, they have certain things in common. And generally they are resistant to corrosion, and they're resistant to chemical attack from most chemicals, including CO2 and high levels of H2S. They're more flexible than steel, about 10 times more flexible, which means that there are lesser forces when you have to install in deviated wells and through kick points. They're very light, especially in drilling mud. The total weight of a composite string can be about a factor 6 less than that of steel. And with composites, you'll be able to log from within the protection of the casing and do the logging you want in reservoir. So how about some composite theory, and why is composite different than steel? Well, first of all, the basic rule of composite means that it consists of more than one material, in most cases 2 materials. The one is the fiber, and then we think about glass, carbon, and there are resins, and those can be epoxies, polyesters. The resin, in fact, is reinforced by the fiber, which is why we refer to GRE, which is glass reinforced epoxy. Now, there's some variables there in the design, and it's the fibers, the kind of fibers you use, it's the amount of fibers you use, and it's the orientation of these fibers in the structure that determine the physical properties of the composite tubular. Composite tubulars thereby are anisotropic. Anisotropic means that they have different properties and different strengths in different directions, which is different than steel. Steel, no matter what way you push it or pull it or load it, it's always going to react exactly the same. But in composites, that's different. And you can actually engineer composites to match any given load case. And engineers need to understand that when you're starting engineering with composites, that it's something that you can make use of. You can make use of the anisotropy of the composite material. So one of the things we have to think about is the fiber layup. And the fiber layup is the term in composite country for the orientation of the fibers. So for instance, if the requirement is very high tensile strength, then what we do is we put more fibers in the axial direction of the tubular. And the other way, if we require high burst strength, then we will position more fibers in the radial direction of the composite structure. And if we want both high burst and high tensile strength, we'll just have to apply more fibers in both directions, which results in a thicker wall of the pipe. Now ideally you would have the fibers to run in the direction of the dominant forces. Dominant forces downhole are typically in the axial direction and in the radial direction. If I can please take you to the slides that you see below. They have 3 bars. The blue one is for a composite structure like Akit can make, where the fibers run in the 0 and 90 direction. So all the fibers run in the axial direction or in the radial direction. And in fact, there's twice as many in the radial direction as the axial direction. A lot of fiber in the radial direction, which means a high burst resistance. If you look at the tensile, you'll see that where the blue bar is taller on the left, on the right hand side, the gray bar is taller. So there's a higher tensile strength for the gray, and the gray has the fibers in the axial direction. In collapse strength, you see there's not much difference between the orientation of the fibers, either radial or axial, and the same goes for compressive strength. The third bar in every diagram is typical for a 55-55 degree orientation of the fibers, which will be typical for any composite that is made with a filament winding technology. And that's the common technology to date before Akit came along. Now on these 4 graphs, you'll see that there are 4 sets of columns, and that represents time. So the first one is instantaneous, 0 hour. Now 0 hour doesn't tell you very much. That's an instantaneous short-term test, and it gives you a certain result. More important and more relevant to you is what happens with time. So the third set is after 15 years, and the last set on the right hand side is 30 years. Now what you see is that with the 0-90 layup of the blue bars and the gray bars, as only Akit can produce, there's little deterioration of performance in time. If you look at the orange bars, the 55-55, you see that there's a much greater deterioration of performance in time, and that all has to do with the fact that these fibers are loaded in different directions than their actual orientation, which results in a lot of internal friction, internal stress in the pipe body. So the conclusion of this slide is, if you have a 0-90 layup with all the fibers in the radial and in the axial direction, you're going to get better performance with time than you would have if the fibers run at a different direction. Another aspect of composites is void content, because ideally a composite is made of resin and fibers, and there's no voids in the composite structure. Now why is that so relevant to voids? In the graph on the left hand side here, you see that with increasing void content on the bottom axis, the strength fraction decreases. So with higher voids, you have to compensate for the strength of the material by degrading it. And very typically at 1 to 3% more void content, the composite structure will be up to 20% weaker. Please note in that graph, what I put in the yellow arrow box, is that this graph has a cutoff at 0.6% void content, because normally manufacturers cannot go below the 0.6% of void content. Now where the graph on the left hand side is one that is instantaneous, it's about at any given time how you should compensate for voids in the material strength. The chart on the right hand side accounts for the factor of time, and what you see there is that when there's 3% voids, 85% of the remaining strength is reached after 1 to 2 years, and after that the material will be even weaker. At 1% void content you can get about 18 years of life before the performance drops by more than 15%. And for a structure with 0 void content, the structure will be stronger than 85% of its original strength up to 70 years. So the factor on the right hand side diagram will overlay the one on the left hand side. So you can get at 2% void content, you may need a strength fraction of maybe 85% because of the voids, and then realize that there's another 85% you have to correct for after about 4 years of life. Microscopic view of a cut through to a composite body, which has alternating layers of glass that are perpendicular to the cut, and those that are almost parallel to the cut, which shows long ovals in the glass filament in plane. And there's a resin-rich area, which is only resin, there's no glass there. Just about the scale of this slide, a typical glass filament will be about 10 to 16 micrometers. So that's about 1/100th of a millimeter. If there were any voids in this cut through, they would show as black. and as you see, there are no black voids in this structure. So how is that done? Well, the process makes the whole difference. Just about every composite tubular is made by the process of filament winding, which is shown in the diagram below. So the fiber runs through a resin bath to get fully wetted, and is then wound around the mandrel very much like cotton on a reel, up and down until you get sufficient glass to give the pipe its strength. Inevitably though, in that winding process, there is going to be an entrapment of air and an entrapment of moisture, because moisture from the air likes to sit on the glass. So that moisture and the air are trapped as small bubbles in the composite structure. And in the bottom you can see that if you have between two different glass fibers, if there is air, if there is humidity, of course you'll get propagation of fluids so much faster. You'll get pressure in those little bubbles from the pressure that's applied within the tubular, and it is going to lead to micro cracking and ultimately failure. This picture shows a typical filament winding operation. A lot of fibers at the same time being wound around the mandrel after being wetted by the epoxy. Now this looks different. This is how Akit makes its tubulars. So this works in a dry state, and the material there is the glass, which has the glass fibers running in different directions in the glass, over which we have full control. It's placed within a mold, and subsequently the mold is centrifuged. It's rotated at very, very high revs to actually create forces of up to 500 G, 500 times the gravity. So after the glass is placed on the inside of the mold, and it will sit against the surface on the inside, then the centrifuge starts. It really starts rotating fast, very high revs, to generate hundreds of G forces. And then the epoxy is inserted in the mold. The epoxy, of course, flies to the outside under centrifugal forces and penetrates all the way through the glass. And because of the spectacular amount of G forces, you find that all moisture and all air is being driven out of the structure and goes to the inside of the mold. And after hardening, what we're left with is a pipe body that is totally free of voids, and the glass sits exactly in that orientation where we've engineered it to be. If you look at some of the technology involved, because Akit is the only company that has mastered this technology, the machines, of course, are not only very complex, but they're also unique, and they're fully automated. And that gives us total control over the repeatability of the process and traceability of the result. As far as testing is concerned, there are a lot of test setups, and many of those were made and constructed because our customers have asked us certain questions and would like certain tests to be performed. And of course, we will readily oblige, because we also want to make sure that the customer has no doubts about the suitability of the tubulars. So on this particular test bench, what we do is we try for wear. So what happens if you would install a casing and then you'd like to drill through it, and you get of the casing and then being rotated? Well, what we saw is that there is hardly any discernible wear after hours and hours of drill simulation. Another test that we did was very similar application. What happens when you drill through the casing and the banging of the tool joints against the inside. So this is a machine where there's an installation which drops the tool joint on the inside of the casing, and we've run that for hours and hours on end, mud in the system. The result was the same. There's no delamination, there's no wear, and the pipe body actually holds up extremely well. But my point basically about this video is, if there's a concern by a customer about a particular property that needs to be tested, then we'll test it, we'll write up the protocol together and make sure that we address any issue. In terms of the installation, all traditional tools can be used, and the connections that we use are very slender. So compared to other composite manufacturers, very often, especially for higher loads, the couplings get very bulky and wide. What you see here installed in a drill rig is a few joints. You also see a centralizer there. There's a wide variety of possible centralizers, either metallic or non-metallic, which can be installed. Traditional slips, tongs, and all the running equipment. In terms of the integrating the composite with the rest of your drill string, there are crossovers from steel to composite, from composite to steel. And those have been tested. They've been tested both in the world record installation at 16,000 feet, but also in drill tests with composite casing drilling applications, which we run together with our strategic partners, HWT. And we've successfully done that in a couple of wells, and there's no discernible wear and tear on any of these crossovers either. But please realize that this is not the end point. Where Akit is now is on the way to something even greater. So we have our entry model, and our entry model is a composite that is 100% void-free. It will last, and it's going to outperform any other composite out there. But there are challenges, of course. We want to have all sizes available, and we want to make sure that the temperature resistance increases. Where we're currently constrained to around 100 Celsius to 114 Fahrenheit, we are underway with plans with strategic partners in a European subsidy project to raise that to about 170 degrees Celsius. And of course, with typical pressures that go with those temperatures as we drill down deeper into the earth. So slowly and with continuing R&D, we'll increase the range and we will increase the performance of the tubulars. And where we stand now is tubulars in a few sizes up to 100 degrees Celsius. So in summary, every composite consists of resin and fibers. The orientation, the structure, and the amount of fibers determine the physical properties. And these physical properties can be engineered to be different in different directions to apply the strength where you need it in your application. Having fibers in the optimal directions, which means parallel to the greatest forces in your application, determines how well the material is going to perform in time. Voids in the structure are always a bad thing. And there's a very distinct benefit of not having any voids in your composite structure. Akit high-strength composite tubulars have no voids, 0.0% voids, and all the fibers run exactly in the 0 and 90 directions, which are the directions of the forces and the pressures in a downhole application. So we have a unique technology that we use, creating extreme amounts of revolutions and g-forces to result in a really strong pipe body, which is engineered specifically for downhole use, because downhole applications is all what Akit does. We're ready for market and we'd like to work together. Plant is fine, the product is great, we have the skills to help you with installing them on site, and we will be really happy to work together.